In this last section of the chapter, we are going to discuss thermal expansion of materials that occurs when the temperature is increased uh, from room temperature or ambient temperature. And the result or the physics behind this is that the materials will expand as heated because the molecules jiggle faster and they move further apart. And this expansion causes, for example, a stretching or elongation of rods or wires um, or train tracks, which are made of iron. And while they are intended to be laid down in very, very straight formation, parallel formation for the wheels to travel smoothly over, um, the increase in temperature can, in fact, cause the expansion of the track, and it will have nowhere to expand longitudinally, that is to say, along the train direction, if they are fixed at both ends. So when it tries to expand, the only thing it can do is to buckle. It expands by bending either left or right of the center line of the track, and this then leads to the observation of the buckling. This would occur, for example, when the track was laid on a cold day in winter, and if we now wait the until the summer, when the temperature rises a great deal, then that thermal expansion cannot be accommodated. Now, one thing I forgot to mention is that when you lay down the tracks, they're laid down in segments, and the segments are usually 20 feet or 30 feet long to be set onto the wooden ground structure and where they're nailed into place. So what we're talking about is the gaps between these 30-foot structures, so which will, if not, provided for, or the gaps are not of spacing is not accounted for, then that buckling that we talked about would take place immediately, or not immediately, but when the temperature is expanded to a very high temperature on a hot day. If, on the other hand, we had spaces between the tracks or the track segments, then they could accommodate the increased length of the track with it, so where the gap was large enough so that the expansion up to 120 degrees would not be sufficient for the ends of the segments to start hitting each other, which then leads to buckling. So a gap is one way of dealing with this. We'll talk further about another technique, which is called the joint, or the device is called expansion joint, which is also shown on figure 1511 of your text. Another example is the warming effect of a lid on a jar. Sometimes we find that jar lids are very tight to unscrew. They're very difficult to unscrew. So if we place them under hot water, hot running water, then we expand the metal lid, and the metal lid will loosen because it has expanded under heat. Now, while it seems very, very likely, or we know that the metal lid will expand, the glass jar will also tend to expand as well. And therefore, we need a reason for understanding why that lid becomes loose when we apply hot water. Well, the answer lies in the fact that different materials will expand at different rates for the same temperature rise. So placing the glass jar with the lid under hot water, the lid rises by 30 degrees of temperature, but so does the glass jar. However, the glass expansion is less than the expansion of the lid, and therefore the neck of the jar does not expand as rapidly as the lid. And when the lid expands, it loosens its grip around the neck, and this would explain what happens. Now, this slide shows exactly what happens to the railroad tracks when they were laid and nailed in place on a cold day, and they did not account for the expansion of the steel tracks, which would occur in the summertime when the temperature was elevated considerably from the temperature at which they were laid. And this, of course, has to be eliminated in order for a track to work in all conditions. So one way they have managed to circumvent this problem is to put gaps in the small gaps in the railroad joint, and that by joint we mean the track is laid down with, for example, in 20-foot sections, but when we lay down the sections of the track, we leave a gap between the two sections, so that when the temperature does get very hot and each of the track segments expand, they will expand only just enough so that they can never quite touch each other. And this is designed by knowing exactly how much they will expand for a given temperature on a hot day, such as 100 or 105 degrees. Places like Arizona, they have to design these so for the worst case scenario where the temperature can reach 120 degrees. So this has to be taken into account. Now, the gaps themselves can actually generate a problem in the wintertime because the gaps will be largest in the winter when the tracks contract. And when the train wheels go over the joints or the region between the tracks, the gap, we should say, uh, it will not be as smooth a ride as in the summertime when they are expanded and the gap is very small. So one way to avoid this is what you would like to do is put in a filler material that will allow for that's more less rigid than the steel, so that when the steel expands, you put in a filler material, it can absorb that extra length without bulging at the surface. So one type of material that is used, or technology, I should say, is the expansion joints. And if you look at Figure 511 on your in your book, you will see that there is a tongue and groove arrangement of this joint that exists between two layers of concrete that is designed to absorb the expansion of the concrete, and therefore allowing the metal structures to come closer together. And the reason they can come closer together is you'll see that there are air gaps, which are dark in color on the photograph, and those air gaps get filled when the concrete pushes the tongue, or we call the tongue and groove of the joint closer together, and therefore can accommodate the expansion without causing the concrete to buckle. So this is one way in which this can be accomplished effectively. In this slide, we examine the consequences of what happens when we have two materials that have different thermal expansion for the same temperature change. Sometimes we call that different rate of expansion. But the basic idea here is that we know that different materials will expand in their length or their area or their volume, but in this case we're talking about length, will expand their length at different amounts for different materials. If they both undergo, we will say, an increase of 20 degrees of temperature. So the property that we want to make use of this, which is in this case, we are going to discuss the concept of the bimetallic strip, is that when we place two materials with different thermal expansions, the brass is cemented or glued onto the iron, and when we place these in contact with different thermal expansions, then we examine what happens to that strip when it is cooled or heated. Now, the basic point here is that brass has a larger thermal expansion than iron. That's to say that if you increase its temperature, its length will increase more than the iron that is connected to it. This then heating effect will cause the bimetallic strip to bend because the length of the strip of brass will become longer than the length of the strip of the iron. And since they are glued together, they have to change their length according to the pressure applied by the brass. In this case, the increased length will tend to elongate it, but the glue joint between the iron and the brass will not allow the brass to just increase in length longitudinally. It's going to have to increase its length by by bending because it is cemented to the iron and it cannot expand without it. So the brass then expands more. The deflection of the bimetallic strip is in a downward direction. And this can be used, for example, if you want to activate an air conditioner. So the idea is that the bimetallic strip will bend in a direction that will connect or close a electrical circuit that is wired to the air conditioner to turn it on. And that switch then activates when the temperature rises above a given point. Now, we don't need a hot flame like a candle to do this. The set point could be as small as 2 or 3 degrees above ambient room temperature, and then you want it to be cool. So to maintain a temperature below 72 degrees, for example, then you want, as you set in your thermostat, then this curvature or bending under heated conditions will be enough to connect a closed circuit or produce a switch that will activate the air conditioning. Similarly, if it gets too cold in the house, the brass is going to contract much more quickly than the iron, and therefore the bending will be in the upward direction, which is shown on the figure on the left. And by doing so, we can then have the ends of the strip made to be in contact with a circuit that activates the heater in the house or the furnace. And so by doing this, using this bimetallic strip, we can either have the bending cause the closing of a circuit to activate the furnace for heating, or if it bends downward, it can close the circuit that will activate the air conditioner. So this bimetallic strip then can be used as a thermostat, and the thermostat can be used to control the temperature in the house. Now, this question asks you to determine or how you would recommend stringing telephone lines between poles on a hot summer day, bearing in mind that things are going to change in a much different way on a cold day, and that is going to cause a change of length to occur. So it'll take a few moments for you to answer this question. Read the answer, and we will resume in a few moments. So just one comment on the last question slide. Hopefully you were able to answer that the way to string the telephone lines was to allow some sag to occur. And as the slide shows, describes, that if the reason you do this, if you are wire setting the wires or laying the wires on a hot day, is that in the wintertime they will contract. So if you string them so they're very tight, then making the not allowing for the contraction of the wire of the telephone line or the telephone wire on a cold day basically will cause the tension in the shrinkage of the line to be such that it will pull on the telephone poles on both ends and therefore can reduce the stability of the structure. So that was the idea, that if you lay this on a on a hot day, you need to allow some sag of the line to compensate for the contraction that will occur in the winter. Okay, now moving on to this slide, we're looking at another example of thermal expansion. And here the general theme is that the expansion in liquids is greater than in solids. And by the way, the expansion in gas materials such as nitrogen, air, oxygen, and carbon dioxide and so forth, those have a much larger rate of expansion than liquids, and liquids have a much larger rate of expansion than solids. So this is the order in which they occur. And the example that's being given here is that the is that if you imagine that you are filling your gas tank on a hot day, and this gas is being stored underground, then when it goes into your tank, it is going to warm up, and it is going to cause an expansion, and one that is in fact going to lead to a problem if you don't have some either enough airspace remaining in the tank or a relief valve that will allow that expansion to occur without rupturing the tank. Now, another reason that this happens is that in comparing liquids to solids, is that the car tank itself is metallic, and it is made of solid, but it doesn't expand as much as the gas inside the tank. And that's what's causing the rise in the level of liquid in the tank. And if that does not have a place to go, then it could lead to a rupture of the gas tank itself. For the rest of this chapter, we are going to examine the thermal expansion of water uh, that occurs under various temperature changes. So up until now, what we have been saying is that if you heat an object up, its volume or length will expand or increase. If you cool the object down, its volume or length will shrink or decrease. And that's generally true for most substances. And in fact, it is also true for water in most temperature ranges. And particularly if we are above 4 degrees Celsius, which is 4 degrees above the freezing point, in its liquid state, all the way up to the boiling point, the liquid does expand as you heat it up. And if you go into the ice phase, the frozen solid phase of water below 0 degrees, it does in fact continue to contract as it cools down. Both of those are perfectly in line with what we've been saying. But the strange behavior of water is that between 0 and 4 degrees, it does exactly the opposite of what we expect. So if we cool water down from 4 down to the freezing point, the volume of the water actually expands instead of contracts. And it's only in this narrow range that this occurs. And it is due to the molecular structure of water that we'll examine in the next slide. But for now, we want to just note that the normal idea of contraction when cooled does not apply to water between 4 degrees and 0. But it does explain why ice cubes float in water. The objects that float on a surface are less dense than the liquids around them, and this is particularly then going to be true for water. Icebergs or sea ice floats on the surface. Icebergs, water, ice cubes will float on the surface of a glass of water because they are less dense. They have this unusual property that that the volume expands just before it freezes, and then when it freezes, it has this lower density, which causes it to float on the surface of water. So the expansion of water as it's cooled from 4 degrees to 0 degrees Celsius can be explained from its molecular structure. And so, generally speaking, without going into too much detail, when water becomes ice, it expands, and ice has open structured crystals resulting from strong bonds at certain angles that cause its volume to increase just before it freezes. So you see here that in the liquid state, the molecules are very close together when it's above 4 degrees, but as it cools down, there is this increased distance between the molecules, which lowers its density. Now, after this slide, I am going to let you answer the questions that follow, and we will let you, you'll have a chance to test your knowledge, and I will make a commentary on this one before doing so. So the point that's made here is that, and as we discussed in the last slide, between 4 degrees and 0, the volume of ice increases. And so, as or I should say, but however, once it does freeze, it does contract, and therefore does exhibit a slight density increase as it cools below 0 degrees. However, it never reaches a density that is higher than the water that it is floating on. So this explains that regardless of how cold the ice cube is, or the ice on the lake, it will always have a density that is lower than the water that it is floating on. So this is just making sort of a further commentary. And again, it emphasizes the fact that below 0 degrees, ice does behave as a normal solid in that it will shrink, and therefore its density, or its molecules or mass per cubic centimeter, will increase as it cools down, and that is normal of all liquids. The only region where it's not normal is between 0 and 4 degrees, where it exhibits this property of expansion, but it maintains the ability to float on ice regardless of how cold it gets after it freezes. So that's an important factor. Generally speaking, the density of ice is about 10% lower than the density of water at the freezing point, and that, of course, is why it floats. So we'll let you take the next couple slides. I'll put some blank audio spacers in there to give you 30 seconds to read and check the answers. And then we will resume on chapter 18 when we're done.